Hello, everyone, and welcome to this edition of Science with QuEra. Today, we're going to talk about an exciting Nature paper, continuous operation of a coherent 3,000 qubit system. My name is Yuval Boger. I'm Chief Commercial Officer for QuEra. QuEra is hosting this webinar series, but for this particular paper, this was entirely Harvard and MIT work. QuEra was not involved in the research. Maybe some financial contribution, but it was not technically involved in the research. But of course, we're very interested in the outcome, and we believe that some of this research can be part, perhaps, of future QuEra systems. With me are three of the authors of this paper: Elias Trapp, Tim Gao, and Luke Stewart. Hey guys, welcome.
Hi.
Hello.
Thank you for having us. I'll give two quick slides on QuEra, just for those that are unfamiliar with QuEra, and then be off screen and let the authors present their amazing work. So QuEra was actually born at the Harvard and MIT. Two Harvard professors and two MIT professors were scientific co-founders at QuEra. The relationship that QuEra has with Harvard and MIT is probably one of our secret weapons. In terms of both scientific collaboration, in terms of, I believe there's some QuEra equipment at Harvard labs. You know, we certainly love to hire Harvard and MIT graduates to work at QuEra. And so there's, and we're also physically close by, just a bike ride away. QuEra is a commercial company. We believe we're the scientific and commercial leader in neutral atom quantum computing. We make computers that are available either on the cloud or on premises. Earlier this year, we raised over $230 million from Google, SoftBank, NVIDIA, and many others. So we're well positioned to take amazing research such as this one and turn it into a working product. And indeed, we are exceptionally interested in neutral atoms because we believe that neutral atoms are really the most promising modality, the most promising way to create large-scale fault-tolerant quantum computers. Let me just give you the reasons how at least we see them. Computers that use neutral atoms, individual atoms, in our case, rubidium, is the qubit. And atoms are perfect. We could take 1 billion atoms and they'll be perfectly identical. There are no manufacturing defects. Every atom is perfectly identical to the other one. Atoms can be shuttled around. So the way quantum computers using neutral atoms work is that atoms are trapped in sometimes what's called optical tweezers, and they can be moved around. And what that means is that essentially you have all-to-all connectivity. You can make any atom, any qubit, be close enough to interact with any other qubit. And this is an advantage relative to architectures such as, say, superconducting qubits, where the location and connectivity is fixed. Another thing that neutral atoms allow you to do is parallel operations. I mean, the excitation happens by shining a laser beam on the atoms. You can have a zone where a single laser beam shines on multiple pairs of atoms, and that's very useful in creating transversal gates and controlling some of the error propagation. Many atoms could be put in a single system. A team at Caltech, unrelated to QuEra, demonstrated, I think, 6,100 qubits on a single machine. This research shows 3,000. And the reason, the reason this is important is that large-scale fault-tolerant quantum computers will need many qubits, and the fact that you can put lots of qubits on a single machine and perhaps defer the interconnection of multiple machines is a big advantage. Last, neutral atoms work at room temperature. There's no need for cryogenic cooling. So indeed, the systems that QuEra makes have very low energy usage, 10 or 20 kilowatts of power, whereas sometimes, as you can imagine, large-scale quantum computers that use cryogenic coolings will take many megawatts of power. So with that, I will hand it over to the first speaker to discuss this amazing work.
Yeah, thank you very much, Yuval, for the nice introduction, for having us. And just go ahead and share my slides. Alrighty. Everybody sees it? Hoping. So again, thank you for having us. My name is Elias, and I'm joined by my colleagues Tim and Luke today. All of us are graduate students in the Atom 2 lab, which is a collaboration between MIT and Harvard. And today we're here to tell you, we're excited to tell you more about our most recent work on the continuous operation of a 3000 qubit system. Now, Yuval has already alluded to that earlier, but kind of to showcase what neutral atoms are capable of, our experiment, just like QuEra's, is a neutral atom platform. So it's worth to maybe zoom out and kind of look into what has been done with neutral atoms over the past 20 or so years. One of these, there's basically three overarching categories. One is the idea of like quantum antibody simulation using mostly quantum gas microscopes. Another one is our approach using atoms trapped in optical tweezer arrays used to realize reconfigurable quantum. And finally, neutral atoms are also used for metrology and quantum sensing, for example, by using optical lattice clocks. A little further down the route of using neutral atoms for quantum processing, there's been a massive amount of progress made in this kind of regime and the overarching quantum processor based on neutral atoms. So many of the building blocks towards that goal have been readily demonstrated. For example, from high fidelity single qubit to 2-qubit gates through mid-circuit operations, as well as to this entire subfield of logical qubits, and then also which also has been recently shown processor in our group and others as well. And coupled to these building blocks is this question of system scalability. This here shows what Yuval was talking about earlier, over 6,000 qubits from the Enders group at Caltech. So and all these combined is supposed to realize this vision of this large-scale fault-tolerant quantum processor. You could ask, okay, great. I mean, these building blocks seem to have been shown, and what is actually missing that makes this a reality? In order to understand this better, it might be actually good to revisit how these machines are usually operated with neutral atoms. So step one is we start with a finite set of atoms and tweezers, usually from a magneto-optical trap. So you like load an atomic gas from background vapor, you make it ultra cold, and then you load individual optical tweezers from it. And then on this set of atoms and tweezers, you perform a number of calculations and measurements. And step two, and you repeat this many times. However, every layer of the cycle will cause some form of atom loss. So as you repeat this for n times, you have a roughly 0.1% chance of actually losing the atom from the trap. And then eventually you simply run out of atoms to calculate it on. And this is really what sets the hard limit to modern neutral atom quantum computing machines. So then to put that into perspective, today, we can run maybe a few seconds up to a minute. That's sufficient to do multiple rounds of quantum error correction. But then towards this, vision of, I guess, useful quantum computing, we would actually need many days of being able to operate such a machine. And here we're using this kind of prime example of factoring a large number via Shor's algorithm. So then the conclusion really is that generally, atom losses set a natural bound to the machine runtime, and we need to figure out a way to solve this like last remaining challenge for our neutral atom platform. And this is exactly where continuous reloading comes in. And the idea is quite simple. We need to replace somehow these atoms that are naturally lost. And this replacement must occur in a kind of during ongoing quantum operation mid-circuit. And additionally, we have to like source these atoms repeatedly from some kind of reservoir. And then the step-by-step looks quite simple. You have to first detect the loss. You need to know where it occurs, of course. Then you reservoir or into a separate tweezer. You have to cool and laser cool the image this atom to verify that actually the usually stochastic loading process was successful into this tweezer, initialize the atom into its qubit state, and finally move the atom back into the computational array at the right location. And these are the kind of steps. And then following exactly this motivation, there's been quite some amazing initial work that executed a certain number at Princeton or the Max Planck for quantum optics in Munich. But this kind of foundational work has really highlighted two of the main kind of key challenges of this continuous reloading technique, which is one, achieving high enough rates of fresh qubits to actually offset realistic losses that occur, and two, replacing those losses without actually losing any of the information by affecting other qubits that are nearby. And that's exactly where our work comes in. So this talk will first start by explaining how we address these challenges one by one and detail exactly what that actually looks like experimentally. In part two, we'll show more of the results on actually achieving a high qubit flux and use that also to assemble a large atomic array. And then finally, we showcase that we can do all this without affecting any of the other qubits that are nearby. So let's pick any other atomic physics experiment. Also, ours starts with tomorrow. Kelvin temperatures to a cloud, but then we combine this interestingly with two of what is called an optical lattice, which basically is an interfering laser beam in 1D in our case that can trap atoms, and we use those two optical lattices to transport this atomic cloud from the Mott region over half a meter away. I will later explain more of why that is useful and why we have two of these, but kind of the way this process would look like is this. So you first start, as indicated here by this red bubble, you first start with this atomic cloud in a Mott, then you transfer that to the first optical lattice, and then you move this cloud to the intersection of the two lattices, where you hand over the cloud from one lattice to the other. And then you just move it the rest of the way. And here, this optical lattice now is static most of the time and acts as a reservoir. Now, this is tweezers, so just above, we have what is called the preparation zone, which is a static array of tweezers where we execute a number of mid-circuit operations we'll get more into later. But to even first get atoms into this preparation zone, what we do is we pierce the reservoir lattice with moving optical tweezers, as indicated here by these red beams that are perpendicular. And then we pierce them and we drag out atoms from the reservoir into the preparation zone. Importantly, we load these, we apply any cooling light here, which is also a novelty of our approach. Now, as we're dragging atoms out of the lattice repeatedly, one can imagine that eventually this lattice will be depleted, and we later will also see that. And this is really where the dual lattice configuration here is very helpful, because as you are loading tweezers from the reservoir, you can in parallel already prepare a new optical lattice reservoir. So basically, this kind of looks like this. So as we are using this reservoir, we can at the same time already start a new Mott in the distant chamber and move it already halfway to a handle point. Basically, we have like another bolt in the chamber as soon as we need it, and we can replace this reservoir in a very fast time scale if it does get depleted. Okay, now so back to our zones. We not only have this preparation zone for mid-circuit qubit preparation, but also on top we have another storage zone, and this is used to like store quantum information. And within the storage zone, we can apply fast single qubit rotations on over 3,000 qubits simultaneously, as well as apply strong light shifts to all these qubits to shield them from scattering with any resonant light that might be nearby. Yeah, so this is kind of completes our kind of approach in our experimental architecture. And I'm sure everybody's dying to see what it actually looks like in practice, which is why we have this amazing image here. So this is a real life proper image of atoms in our machine with the distances indicated. This is an averaged image, and you can clearly make out the lattice reservoir, the preparation zone here, and the storage zone here. And then in the future, we'll also add a dedicated entanglement zone for 2-qubit entanglement, as well as a readout zone. And then that, I think, more resembles the quantum processes that most of you will be familiar with. Now, this leads us to part 2, actually using this apparatus and characterizing what we can achieve with this design. But first, we'll focus on this high flux reloading and then use that to assemble a large atomic array. I already talked to you about how we actually load atoms in the first place. So basically, we have the reservoir over here, and then we just pierce the tweezers and drag it out. That was a very fast process, and we don't have to apply any we can do this many, many times. We see that these extractions, these repeated extractions, are kind of dragging out tweezers, and this is kind of very impressively shown here, where this is a fluorescence image of our optical lattice reservoir. So here for like 0 extractions, and as you continue extracting for many times, it's kind of funny. You see here this kind of square bracket that you extract. We basically just deplete the reservoir in the location where it actually looks like in numbers. So what we do here is we just bring in one reservoir, just keep it steady. What we extract, so in order to count the number of atoms obtained from the reservoir. Then what this looks like is sort of like this. So as a function of the number of extractions, you obtain a net number of atoms and tweezers from the reservoir. And this really characterizes the capacity limits of any single reservoir that we're using. There are 2 observations here. One, as you extract many, many times, the success probability of loading atoms into tweezers decreases. So here the gray line indicates a 50% filling fraction, which is what you would stochastically expect if you load a tweezer from basically any source. And you can tell that after about 50 or so extractions, we kind of deviate from this line quite significantly, because basically our loading just saturates. This makes intuitive sense, because as we're depleting atoms, you have less and less there, so your probability of loading them is small. And the second observation is kind of equally interesting, is that at least over the first, let's say 50, 30 or so extractions, as shown on the right, the reservoir actually is a really nice way, or this optical lattice reservoir is a nice way of loading tweezers, where we have like consistently saturated 50% loading. And this really establishes the lattice as an atomic reservoir. Okay, so then now in a second step, we use this dual lattice design to overcome exactly the saturation limit of any single reservoir that I was just showing, that we observe. And we do this by basically bringing in a fresh reservoir and replacing the one that is currently in use on a much faster time scale than that it is depleted. And this is kind of the time sequence for this process. So we still have the reservoir here, and we still, extract and image atoms. But then at the same time, we already are starting a monitor in this distant chamber, and we're just reloading and transporting the first optical lattice and bringing it to this handover point I was just telling you about. So then once the first optical lattice is ready, it just kind of sits here, and we then decide when we want to replace the original reservoir, whenever it's like sufficiently depleted. And the magic of this is really that it all runs fully in parallel. Basically what I'm saying, like we put another bolt in the chamber and use it whenever it's ready. So then now we do the same thing as I just shown for a single reservoir. So we extract atoms and we count them, but at this time also replacing reservoirs in parallel as they are depleted. And this is what it looks like. This is what that looks like. Again, 2 things to notice here. One, mind you, this is a log scale. So the stream of atoms here is actually linear. This is contrary to the single reservoir case where we see a depletion. And 2, you see here these small interruptions here. And that is because it takes some actually finite time to bring in the final reservoir, about 20 milliseconds or so, which in this time there's no reservoir present. So then you can't load any tweezers from them. But this is not a problem, as we will see later. So it's fair to say, like as is, by replacing reservoirs, we can overcome the kind of the saturation of a single given reservoir, this limitation, and we can achieve 300,000 single atoms and tweezers per second. And this is something we can in principle run forever. Now, atoms are nice, but actually what we care about is qubits. So we have to make these atoms into qubits. And so instead of just extracting and imaging in a very fast time, which consists of not only extraction, but also a dedicated parity projection pulse to ensure single site occupancy in our tweezers, we hand over to a more stable SLM tweezer array, and we optionally rearrange and further laser cool and finally initialize the qubit state. So then once you do all this kind of long sequence, if you then count the number of qubits you actually obtain, we get these. Oh, actually, very importantly to mention here, this qubit preparation sequence was significantly shaped by a few of our co-authors. So then once you then execute this sequence and count the number of qubits, we get these two lines. Now the green is where we just initialize the qubit state of unsorted qubits. So the array would have defects, which in principle is not a problem. And the orange is when you also rearrange the qubits into a defect-free array, which takes some time, which is why the overall rate is lower. But importantly to say, since the qubit preparation sequence is in every case longer than it takes to bring into a reservoir, this is fully continuous. You see there's no interruption anymore. And then in total, we can claim we can bring in 300,000 atoms per second and 30,000 qubits per second continuously without interruption. And the way this kind of looks like is something like this, where this kind of movie here that in real time shows atoms being drawn from the reservoir as fast as we possibly can. And importantly, just to stress the fact, these are not atoms, these are not the same atoms. We bring in new atoms every time, and this is kind of how fast we can do that. And now Tim will tell you more about how we can use this high flux to assemble and later maintain a large-scale atomic array.
Cool. I guess just a little bit of brief comment there. This atom movie that Elias just showed, I think there's some internet lag. So from my side, it looks a little bit slow. In fact, in reality, in the actual video, it's much faster. It's just that it's some internet lag. Anyway, thanks, Elias, for introducing our project and as well as explaining the atom reservoir. So in my part of the talk, I will mainly focus on scalability aspect of our work. And to me, I think scalability is one of the most sort of the main remaining challenges for reaching useful quantum computing right now. And here we make progress on scalability in both the spatial domain as well as the temporal domain. So what do I mean by spatial and temporal domain? In the spatial domain, basically we assemble an array of 3240 site with high filling fraction. And this indicates a progress towards larger scale quantum computation. Basically, if we have more qubits, that means we can encode more information and we can do more complicated quantum states. And in the temporal domain, we showcase 2 hours of continuous operation, and this indicates a progress towards deeper quantum circuits and longer computation. So we can run more complicated algorithm to run for a long time. And here I will first discuss a little bit about the spatial domain of scalability, how we assemble the large array. So this is a fluorescence image of the zone architecture that Elias also showed. We have 3 zones. Here is the lattice reservoir that he just talked about. On top of that, there are 2 tweezer zones controlled by 2 different SLMs. And then in addition to that, we have a set of AOD tweezers that are moving tweezers. Basically, they are moving across the zones in charge of transporting atoms and sorting atoms. And for those who are not super familiar, SLMs or AODs are standard equipments in our field, like optical equipments that are in charge of generating tweezers. And here is a simple schematic of our optical setup. We have 2 SLMs, 1 pair of XY AODs, and combined into 1 microscope objective that is in charge of generating the tweezers. And we have another microscope objective in charge of imaging the atoms onto the camera. And we have 3 high-power lasers for large tweezer array generation, 1 for the storage zone, 1 for the preparation zone, and 1 for the moving AOD tweezers. I would also like to highlight our microscope objective. I think it's a little bit special because it has a large field of view of more than 1.5 millimeter in diameter. So as you can see, our current setup already spans 600 micron in the atom plane. And this is already larger than most of the atom array platform in the world. And in the future, this large field of view of 1.5 millimeter can also enable us to incorporate more zones and more tweezers into our system to demonstrate even more scalable quantum computation experiments. And when assembling the large array, we are facing a few challenges, and I think it's kind of true for like all kinds of human endeavor. Is that like if we have scalability, then we need to suffer in controllability. Basically, there's a trade-off. Larger system harder to control. So here we suffer from that as well in terms of building the large array. So the first one is overlapping the large tweezer array is already a bit tricky because we have the static tweezers that are forming our zones, but we also have the AOD tweezers that are transporting atoms between the zones, and we need to have them hand over atoms between each other to finish the transport. And to do that, we need to overlap the tweezers very well. And for large array spans, nonlinearities will cause non-uniform tweezer spacings, so which will cause overlap to be not good. And another challenge we face is trap depth inhomogeneity. Basically, our SLM is a diffractive optical element, and its diffraction efficiency drops as you get further away from the center. So if your array has a large span, then the trap depths will not be like the intensity of the optical tweezers will not be the same across the array. And to solve both of these problems, we basically implement some automated algorithm to do like side-by-side measurements of the tweezer position here or the trap depths here, and then use it to feedback onto our tweezer generation algorithm to control the tweezers well. And in addition to that, we also face another trade-off, which is one of it is a limited optical power. So here, when I say limited optical power, I not only mean the output power of the laser itself, but also the SLM has lower diffraction efficiency. And to make things worse, we have a large array, so the span is large. So as you get further and further away from the center, the diffraction efficiency will even drop like significantly. This is a plot that the vendor sent us. As you can see, diffraction efficiency drops as you go farther away from the center. So this seems to indicate that we need to pack our array as close as possible to stay near the center, so that we save on diffraction efficiency. But we cannot do that because we also need to transport atoms through the array, because when we move through the zones, the atoms need to transport through the array. And if the arrays are too close to each other, the spacings are too small, then the transport atoms will have some crosstalk with the static tweezers nearby. So then basically, as you transport atoms through the zones, it will incur a lot of atom loss within the static tweezer array. And to solve this kind of trade-off between trying to pack the array close or to try to separate them farther away, we basically designed this like special geometry, which has like close spacings normally, but once every 2 columns, we leave a wide channel for atom to transport through. So this enables us to pack the array as close as possible while leaving channels for atom to transport. And now I explained I've already explained the setup, the geometry. I will go to actually explaining the procedures of assembling this large array. So as Elias was talking about, we have this nice atom reservoir, lattice reservoir, and then we can load atoms from the reservoir with high flux into the preparation zone. And then we take some time to do row by row sorting in the preparation zone so that the array go from stochastically loaded to deterministically loaded. So now we have a defect-free array. So here is a single shot image of our preparation zone. We rearrange into a 600 target size once every 2 columns. And as you can see, there's no defect across this array of target size of 600. And then on average, so normally we rearrange to a 540 size, and on average we have 99.6% rearrangement fidelity here. After that, we move the defect-free array from the preparation zone into the storage zone to assemble the large atom array. And we divide the atom array and the storage zone into 6 subarrays. Each subarray is indicated by a different shades of blue here, and they're also labeled numerically here. Here we're assembling the second subarray, and in total we need to do 6 iterative steps to assemble all 6 subarrays. And the result of which is a nice large array. Like here, there's a single shot image of 3217 atoms with which means 99.3% fielding fraction. And to the best of our knowledge, this is the largest high fielding fraction atom array in the world. So this indicates our progress towards more scalable, larger quantum system for our platform. And on average, we have 98.5% filling fraction for our storage zone, and which means an atom number well above 3000. We also reuse the lattice reservoir during assembly, sort of like what Elias mentioned earlier. We don't just use the reservoir once. We can, for example, use the same reservoir to assemble the first and second subarrays for the experiment and then bring in a new reservoir. So here is a atom movie that is kind of better explain the procedure. Basically, we first assemble a defect-free array in the preparation zone, and then in 6 iterative step, we build the storage zone array. So the third subarray, the fourth, and the fifth, and the sixth. And note that this is real atom image. So each frame is a real microscope image of real rubidium atom fluorescence. Yeah, and then this is basically our procedure. And now I shift towards the temporal scalability aspect of our work. So here we show that we can maintain an array of 3000 atoms for over 2 hours. And the way we do that is that we need to fight against atom loss. And the way we do that is that we throw away the oldest subarray, which has already accumulated some atom loss. We throw it away and then replenish with a fresh subarray that has high filling fraction. And we just keep doing that for each subarray. And as you can see from the movie, basically you throw away the first one, replace, second one, replace, throw away the third one, replace with fresh atoms, throw away the fourth one, the fifth one, and then the sixth one. And then we just keep on doing this loop almost forever. And then just continuously maintain this 3000 atoms array. And here is a plot of our data. Basically, if you don't do anything, your array will basically disappear in like 2 minutes due to a tweezer heating induced atom loss. So basically tweezer heat the atom up and then atom will escape the traps in 2 minutes or so. But by doing this continuous operation, we constantly replenish with new fresh high filling fraction array. We can maintain this 3000 atoms for more than 2 hours. And this indicates our progress towards longer computation scalability in the temporal domain. And of course, this will be useless if every time we replenish the one subarray, we destroy the coherence of the remaining atom qubits. So with that, I leave the presentation to Luke, who will talk about the coherence aspect of our experiment.
Great. Thank you, Tim. So far, we've heard from Elias about the, excuse me. Here we go. We've heard from Elias about the design of the experimental architecture and high-rate qubit reloading. We've also heard from Tim how we can use this reloading functionality to fill and maintain an array of over 3000 qubits indefinitely. However, if we want to use this reloading protocol to continually supply fresh qubits as part of an ongoing computation, we need to demonstrate that an ability to preserve quantum information on an existing set of qubits while the reloading process is occurring. As we saw, each step of the reloading procedure involves a sequence of operations, including parity projection, imaging, and cooling. Now, each of these, as well as some state initialization to prepare our atoms in the qubit subspace. Each of these steps involves near-resonant laser light in the preparation zone. Now, if we attempt to store coherent qubits in the storage zone without some measure of protecting them from this near-resonant light, we see that the steps of the preparation sequence, although spatially isolated from the storage zone, are still causing decoherence, a destructive impact on the decoherence. Right. So if we look here, we see that our T2 time, standard, our sort of reference T2 is over 1.3 seconds. And if we perform concurrent qubit reloading procedures, our sort of preparation procedures here, we find that the coherence of our storage zone qubits decays immediately, and it's a very dramatic impact. Now, to reliably preserve quantum information on our storage zone qubits while reloading, we need a way to protect these qubits from this resonant light. So the solution that we came up with is to shield these qubits with light. Our colleagues and joint advisor at MIT demonstrated in this paper a site-by-site resolved basis where each atom in their array can be selectively shielded. We choose a different strategy. So in our storage zone, we introduce what's called a top-hat beam, which illuminates all atoms in this zone. We maximize the homogeneity of this beam and empirically optimize the power and wavelength to achieve the best protection results. Now, the key idea with the shielding light is that it shifts the excited state here of atoms in the storage zone to prevent interference from the 780 nanometer light that is involved in our preparation zone operations. It's tuned specifically to be resonant from 5p 3/2 to a 4d 5/2 transition. Now, because the shielding light shifts the excited state of the atoms whose ground state encodes their ground state hyperfine qubit encoding, contains this valuable quantum information that we want to preserve, we protect this by limiting excitations of these atoms. Now you see here, as we introduce our shielding light and at the same time run our concurrent qubit prep operations, same as in the above figure, our qubit coherence in the storage zone is essentially fully recovered to over a second of coherence time, despite our concurrent reloading operations. Now, with the ability to preserve quantum information through the reloading process now demonstrated, we started by maintaining classical bit information. By preparing qubits in one of two computational bit states, either a 0 or a 1, at the end of our preparation sequence, and checking that the array averaged polarization contrast is maintained through time. Now, what does this mean? Essentially, we just want to show that we can maintain our, again, classical bit information, so a 0 or a 1. So this means that if we put all atoms in state 0 in our storage zone and then execute this iterative reloading procedure, do those atoms, let's say, does the average state of the array stay in either its state 0 or state 1? It's the exact same reloading, rearrangement, and transport procedure as we saw before. In the absence of reloading, our characteristic T1 time, so depolarization timescale, is roughly 12 seconds. This is if you just hold the atoms there and don't do anything. With our iterative reloading procedure, in combination with our shielding light on the storage zone, we see that the array averaged contrast stays extremely high. And this is because, again, these qubits are protected. Now we can also demonstrate that we maintain an array of coherent qubits indefinitely. So not just the 0, 1 bit information, but we also want to show that we can maintain the fully describing phase information of each of these qubits. In addition to the shielding in the storage zone, we now operate single qubit gates with optical Raman light to perform dynamical decoupling, which preserves the coherence in the presence of noise. The qubits undergo specifically these XY16 dynamical decoupling sequences for the roughly 80 milliseconds that a single round of the preparation procedure takes. And again, we see that the array averaged now coherence contrast is maintained at quite high levels. Now, there's something else to see here, which is very interesting. If you instead analyze your data to look at the subarray basis, you see immediately a sort of important implication of our iterative reloading procedure. So each gradation of color here corresponds to a separate 1 out of 6 of the subarrays that we use to iteratively reload our large, storage zone array. And you see that these are each undergoing some characteristic dephasing as time goes on. And for the sort of time it takes to do all 6 iterations, we then, for example, replace this subarray with an array of freshly prepared coherent qubits. Now, the gray line is just our control, so no reloading going on. What is our background T2 reference in the presence of shielding? And again, this is over a second. And the important part to recognize is that each of these subarrays, in the presence of the preparation steps for the next subarray replacement, are dephasing at exactly the same rate as the control in the absence of reloading. And so the reloading process overall has a negligible impact on the coherence of our storage zone qubits. Now, if we take a slice at a particular time, right, through and look at what is the state of coherence of our storage zone array, we see kind of a characteristic coherence contrast where the, let's say, darkest curve here, which has the least amplitude, is the next to be replaced and has undergone the longest time of coherence preservation. This just matches, again, the background dephasing. And then the lighter one would be the most recently replaced. And so you see this kind of characteristic gradation of coherence just due to the background dephasing that is naturally occurring on a timescale of greater than 1 second, which is one of the very nice aspects of our neutral atom hardware. So to summarize, we have a few key achievements here. As Elias nicely described, we have a sort of a brand new experimental architecture with a number of nice features that allow us to demonstrate this coherent and high rate replenishment procedure. We showed that our atom supply is extremely high flux. We can operate this reloading procedure to have 300,000 atoms per second, 30,000 qubits per second, and 15,000 rearranged qubits per second. We constructed to date the largest rearranged array of over 3,000 atoms with near perfect filling fraction. And finally, we showed that we can in principle operate coherent operations on our storage zone for an indefinite interval, right? Because we can maintain coherence of these atoms and isolate them efficiently and effectively from our reloading zone operations. So I want to now give you now that we've described our core results, I want to discuss how they integrate and inspire a vision for running long logical circuits on neutral atom hardware. So in a separate apparatus, our colleagues demonstrated several core components of such a fault-tolerant quantum processor. Their experimental architecture seen here is very similar to ours, with the addition of this entangling zone to operate your 2-qubit entangling gates. This is something that we are working to integrate currently. Furthermore, they adopt this logical teleportation strategy, which involves teleporting quantum information from one logical qubit to the next. In practice, this means you're switching the information from a set of older qubits to a set of freshly loaded and initialized new qubits. Now, this sounds very familiar with the approach that I've been discussing thus far. And so now we can see that there's a number of key advantages here, and I'll get to that now. So first of all, this approach minimizes the propagation of errors, right? These errors tend to be left behind through the teleportation step. Once the logical information, the qubit information that we care about as part of our ongoing computation, is moved from the old atoms to the new ones. Now, our colleagues also demonstrated a method for mid-circuit loss-resolving qubit readout and reuse. So this means that we can efficiently distinguish between the qubit state 0, 1, and the qubit being lost. This information is extracted from the teleportation steps and used in our decoding mechanisms, right? Which is specifically identifies the precise location of errors, or loss errors, in a method that's known as erasure conversion, which has a number of important benefits for our overall threshold of our computation and the likelihood of success at the end of the algorithm. Finally, this procedure interfaces naturally with the core advantages of our neutral atom hardware. We can do a number of things very efficiently on this type of platform, including parallel motion of many qubits at once, transversal gates, which involve pairwise operations between two sets of, for example, logical qubits here, and measurements, specifically our loss resolving readout. However, right, atom losses play a major role in these experiments that our colleagues have completed. We see immediately that the circuit depth, right, at which we can operate is directly limited by the atomic reservoir depletion. So our results here amount to a proof of principle demonstration of a key subroutine as part of this long-term vision for deep logical circuits. This is a necessary feature to as we seek to extend our possible algorithmic runtime to the extent of hours and days that are projected to be necessary for the types of computation that quantum computers, have substantial kind of promise to execute. It's finally important to recognize that the reloading rate sets a fundamental bound on your system size. It's essentially a fundamental system parameter. Now, specifically, it sets how many qubits can you operate in parallel, right? So, for example, if we take our current reloading rate of 15,000 rearranged qubits per second, and we make some assumptions about our current Rydberg fidelity and assume a 1 millisecond duration per gate layer, this converts to about enough reloading to offset the loss associated with close to 10,000 physical qubits. With a sequence of realistic upgrades that we make to our system, including an optimized rearrangement protocol, doubling the tweezer power, and improving our Rydberg gate fidelity to 99.9%, all of which should be in reach. We expect that we can increase our reloading rate by a factor of 5. Right. And so now if we again do some basic projections to figure out what kind of logical quantum computations could this reloading rate support, we find that we can start to think about a regime of several hundred surface code logical qubits, for example, each operating with a logical failure rate of 10 to the minus 8. Now, I want to emphasize that as error correction and software continues to develop equally rapidly, we can start to think about things like high rate LDPC codes that are likely to enable even further improvement. This is just to give you a sense of the fact that our reloading rate is starting to, aim towards or point towards a regime where the size of the system and the logical failure rates are approaching the kind of sort of beyond NISQ era regimes that we aim to target. Finally, I'd like to thank all of our teammates and collaborators, especially everyone in the Atom Array 2 team and our joint co-advisors, Misha, Vladan, and Marcus. We have benefited also greatly from our collaborators in our sort of sibling experiment, and look forward to future projects. Thank you for joining.
Thank you very much, Luke, Elias, and Tim. A couple of questions that came from the audience. The first question is, what is the primary challenge at this stage with the qubit preparation storage procedure if we wanted to increase the coherence time beyond currently 2 hours?
I'm happy to take this. So firstly, maybe important to say it's not coherence time for 2 hours. We just maintain the array of atoms for over 2 hours. And secondly, there's no direct challenge we foresee here that would limit us to only 2 hours. We could run this for basically indefinitely. The only challenge that we see currently is that like slow drifts, temporal drifts, and for instance, beam alignment, beam pointing, or as well like what Tim talked about earlier, the overlapping the many sets of tweeters that we have in our experiment. These will naturally drift as the system thermalizes, and this over like a course of a day or two would affect how well we can keep an array alive. But there's nothing you can calibrate away, so we don't really envision any big challenge on extending this further. Thank you.
In the department of Give Me More, why 3,000? Why not 5,000? What's the limiting factor there?
So I can take on this. I think laser power is a limiting factor. We're limited by a finite laser power, but I think nowadays laser vendors are progressing in a remarkable speed in delivering higher and higher power lasers. So I think that's a good thing. Also, as I was talking about, this diffractive optical element that we're using has low diffraction efficiency, especially for larger array. So those are some problems that maybe those vendors can solve, and also we can also be smarter on how we use this kind of equipments. Like, for example, we designed this geometry, and maybe there are more games we can play to squeeze out of this like finite laser power. So I think those are the limitations here.
In the objective that you showed, the 1.5 millimeter objective is good enough, I guess, for more qubits, right?
Yes, it is more than good enough for more qubits, yeah.
Another question for the audience: why must the shielding light need to be a top hat? Does the shielding light alone, without the reloading sequence, also introduce degradation in T2?
It's a great question. So the shielding light we designed to be a top hat because we want to ensure a sharp isolation between our storage zone and our preparation zone. Right, so we find that if there's even a small amount of leakage of this shielding light into the preparation zone, the sequence of operations, including parity projection, cooling, imaging, and state preparation especially, rely on precisely resonant or near resonant light in the preparation zone. And so if we even have a small amount of bleed through, right, of our shielding light into the preparation zone, all of those more sensitive operations become affected. And we can, for example, we are hindered in our ability to efficiently prepare our qubits with high fidelity. So we want to have a sharp separation between our shielding light and our storage zone and prevent as minimal interaction with the preparation zone as possible. And I think I'll say a second point about that, which is that because the shielding light is resonant from our 5p excited state to an additional excited state, it actually interacts extremely weakly with our qubit encoding in the ground state. And so we have a Hertz level shift of our qubits in the ground state. Those essentially don't care about the fact that there's now no excited state transition. And our, for example, optical Raman and the various other techniques we use to preserve coherence operates essentially as if there was no shielding light involved.
Another question, which some would call the $1 million question, if laser power becomes a limiting factor at 3,000 atoms, how do you envision making a 1,000,000 atom quantum computer?
So I think there are a few different approaches, and I don't know which one I personally support, and I think there will be more ideas coming up in the future. So first of all, obviously, laser power can be improved, right? And if we utilize the laser power more efficiently, we can definitely have a factor of like even factor of 10. We can envision that kind of improvement there. And then separately, I think maybe QuEra is working on similar things. Definitely, Luke group, we're working on this kind of photonic interconnect that connects different quantum computers. So for example, you can envision like one chamber having like 10,000 to 100,000 atoms or qubits, and then you have like 10 to 100 such nodes, and you can connect them together, and then they can distribute a computation. So in total, the whole system is like 1,000,000 qubits, but like not a single vacuum chamber can host 1,000,000 qubits. So I guess there are some approaches that I got exposed to. Maybe there will be more ideas.
Very good. So I see that there are no additional questions. Thank you. Oh, there is, sorry, then it looks like there are no additional questions. So with that, thank you very much for the great presentation, and thank you everyone for joining us. Please join us for future Science with QuEra episodes. Enjoy the rest of your day.
Oh,
Thank you for having us.